Well, 23 part A. What is the conservation of momentum? How can we explain that? Conservation of momentum? Anybody? Bueller?
There's no energy loss.
Oh.
Absolutely.
Break it down, hang on. Conservation of momentum. So what does the word conservation mean? Keeping the same, not changing. What does momentum mean? Yeah, but even just like the formula, what's the formula for momentum? No. Momentum. Wake up. Force multiplied velocity. So, no. So conservation of momentum means that the momentum is not changing. But what is the situation where you use this? For what type of situation? For collisions, when things crash. So what you could say, conservation momentum, you could say that the momentum before a collision should equal the momentum after the collision. That's one way to say it. Or you could say it other ways too. But if you all understand my sentence, I'll just use that. Do you understand what I'm saying? That the momentum before a collision, or not even, it doesn't even have to be a collision, the momentum at one point in time equals the momentum at another point in time, as long as there's no outside force. Okay? So, if no force from the outside acts on a system, then that means the momentum will wait, before you write that, I want to write the total momentum. The total momentum will not change or be unchanging or be constant. So if no force from the outside acts on a system, then the total momentum will not change. So it's not really true right now in this room, because as I'm moving, I'm using force from my arms, muscles, and so on. And then it's not really true if I drop something, because what force is pulling it down? Gravity. But when you have like a car and a car, and they turn their engines off, so the engines are off and they're just rolling, then you have conservation of momentum. Yeah? It's important that you understand when to use conservation of momentum. Do you understand when to use it? Yeah? Now, the B part.
For real life, it's difficult because we have friction.
Yeah. You see, you wouldn't really get much opportunity to use it because of friction. Yeah. Although, I think in the second example here is a good situation of when you can use it, because they're talking about atoms. So there's no air friction for atoms because they're so small. There's no air really. They are the air, so to speak. Yeah, yeah. B. So what you have is you have uranium-238. Now from chemistry class, what does it mean to say it's 238?
1 mole.
No, forget about moles. No, don't. No. Your chemistry needs brushing up.
Nuclear.
The nucleus has 238 neutrons and protons. So this is, Lorraine will be so angry at you. 238 is the atomic mass. So there's 238 protons and neutrons in the nucleus. Then what happens is a piece breaks off. So now you're left with 234, and then you have 4 proton and neutrons exit. So that's what the picture looks like. It starts at rest, and then there's like a little explosion, a little bit kicks off.
No, I understand.
Now you understand?
A little bit.
A little bit better? Okay. The name of this is called, well, this one here is uranium, and this one here is thorium. This one here is uranium. And this one here is called an alpha. Don't worry, this is going to be done in semester 2. You don't need to know what these things are. Part 1. Explain why most of the kinetic energy is in the alpha particle.
So I don't know what's happening.
Right. Watch carefully, right? You have 238 protons and neutrons. They're all sitting together like this. This is called uranium. Then all of a sudden, 4 protons and neutrons exit. They just like leave. So you're left with 234.
And it changes its name.
And now it's called thorium because there's less, it's not the same atom anymore. So, first part is, why do you think most of the kinetic energy is in the alpha particle instead of the thorium particle? Or another way of saying it, why do you think most of the kinetic energy is in the alpha? And why do you think the thorium has very little kinetic energy?
Because it's alpha, it's the result.
Yeah, that's one way of thinking about it, yeah. Come on, sit over there. Come on. Go around the other way. Yeah, you're saying that it's result, but maybe we can expand on that a bit more.
Because the velocity is more than the alpha, because kinetic energy is half mv squared. The weight.
Yeah. Still, I don't know.
The weight, because this one's moving slow.
I know it all feels like it should be, but they're looking for the reason why. Like, why is the big one moving slower?
Because it's heavy.
Yeah, so it's like the big one's moving slower because it's the big one.
Yeah.
Like, can we maybe...
Because of the force acts more to the alpha.
Yeah, I think we're getting close to it.
Maybe like that.
So you're right, you got the right idea. When the alpha gets kicked out, because its mass is so small, it can be going very fast. And kinetic energy depends on v squared. So if you were to look at the formula, what's the formula for kinetic energy? It's a half mv squared. So whoever has the bigger velocity will get much more kinetic energy because the v is squared. So I think this is key. And also this is small, so it can be traveling very fast afterwards. So anyways, we'll just say the alpha will be ejected at high speed. Therefore, its kinetic energy will be great. Since kinetic energy is a half m, and here's the key thing, so I'll highlight in red, squared. Half m v squared. Sorry, try that again. V squared. Okay,
Will be what?
will be great. as in large. Now, the next part is show that 98% of the energy is in the alpha. So if 98% of the kinetic energy is in the alpha, 2% is in the thorium. Okay. Firstly, we shall use our conservation of momentum. What's the momentum at the beginning, before they separate? Zero. Okay? Now, if you look at your calculator, and maybe you know from chemistry class, the mass of a proton or the mass of a neutron is roughly, well, the letter we use is roughly U. It's on your calculator.
It's 27.
No. It actually looks like it's 1 and 2. Mass of proton, mass of neutron.
Yes.
But anyways, if I look at the formula book, if you look here,
It's 1.66.
Here.
Yeah, it's 17.
yeah,
Yeah, 17.
it is 17?
Yeah.
Oh yeah, that is 17. Anyways, you don't actually need to put in what that number is because it'll cancel anyway. So I'll just write U. So 234 of these and then 4 of those. So what's the momentum of the thorium? It'd be 234U times V1 plus 4U times 4U times V2.
So
Yep.
why the U is constant? Because like 2, 3, 4 is like there's half of them, not half of them is proton.
No, I know. For this calculation, the difference between the two is not going to affect the answer much. Like, so if you were to do it, it's too small. So like the answer might be 98.05 instead percent. You know, it's not going to matter for this. Besides which, we don't have a periodic table, so you know you wouldn't know how many protons and neutrons is in the thorium, and you don't even know. Now I know, and you'll know in semester 2, but you don't know yet how many of those 4 are protons and neutrons anyways. So we can just say approximately they'll all have the same mass, but I know a proton and neutron don't have the same mass. But roughly they do for this calculation. Anyways, this here, what's the problem with this? What can we find the V1 and the V2? No, we can't. The best we can do is we can say V1 equals minus 4U over 2, 3, 4U V2. So the U's cancel. So the very best we can say is V1 is minus 2 over 117 V2. That's the best we can say. And the minus is there because they're going in opposite directions. Now, what other equation?
98%.
Well, that's what we're trying to get to. We can't use that. We have to try and get to that answer. Yeah. So what we do next, we need to calculate how much kinetic energy the alpha particle is compared to the total. So what would that be as a fraction if I wanted it as a percentage? Multiply 100%. Well, at the bottom you put the total. So that's the kinetic energy, no, the total kinetic energy. So that's the kinetic energy of the thorium plus the kinetic energy of the alpha, and then what would go on top here?
Kinetic energy of
The alpha. Yeah.
not uranium.
No, it's, well, you could do it, and then your answer would be 2%, it should be. Because they want it as the percentage of the alpha. So it'd be we're trying to get to 98. Okay, let's plug in our numbers. So on the top, it's a half. What's the m for the alpha? For you. And the velocity? v1 or v2? No, v2 squared. Now, what's the kinetic energy of the thorium? That's a half. What's the m? 2, 3, 4. Come on, wake up, please. And what's the velocity of the thorium?
-2.
No, just give it to me as the original. v1 squared. Plus, now, the alpha. A half m. What's next? v2 squared. Multiply 100%. Okay. Now, something cancels here? What cancels? The halves, firstly, yeah. What else? The u's. So you're left with this. But you know, you have this formula v1 equals minus 2 over 117 v2. So you can write this as 4v2 squared. But this one you can rewrite as, what did I say it was? Minus 2 over, what was it? Come on, what was it? Minus 2 over... 117, yes. 117 v2 squared plus 4 times v2 squared times 100. Now what cancels now? What's in all of them now?
V2s and squared.
The v2's cancel. So you're left with 4.
But instead, shouldn't you have 1 V2?
What?
You cancel the square only, right?
The v2 squared.
Yeah.
Yeah? There's a v2 squared and everything.
Oh,
Yes, isn't there?
yeah.
Yeah, that's right, there is.
But there should be one more V2 squared.
Where?
Oh, no, sorry.
Don't hurt your teacher. 2 over 117. Oh, sorry, I lost my 234 when I was carrying it down here. There's still a 234 there. It's a half m v squared, so there's still a 234 there. I was wondering why my answer didn't match up. So don't forget that there. I'll circle it in blue. Okay, let's type that again. Yeah, so you see, Andy, this is, for me, 98.3%. Although the question does say, show that more than 98%. So any answer a little bit more than 98 would be acceptable, really. So that's 98.3%. Mm-hmm. I'll zoom out a bit. Yeah? Okay, let me just snap this one here.